being with you guys. My name is Carlo. I'm a senior lead solution architect at Cartesi. And today we're going to talk about how can we do things using our tech, right? So basically what we will cover is an overview of Cartesi, an overview of how you can develop with it, and I'm going to do some comparisons on how you do Web3 development, Web2 development, and then how you do it with Cartesi, right? And a quick intro to Cartesi Rollups, which is the product we use for enabling our tech. So just an overview of what this stack is about is this. So basically the objective is having this really rich code that you can use for decentralized applications. So if you develop on Solidity, you probably have faced a lot of issues like the size of the transactions or lacking libraries that do stuff that you're usually doing on Web2, like parsing a string or something like that, accessing the database, all this stuff. And that's what we want to bring. We want you to have the same power and expressiveness and computational power that you have on Web2, only available on Web3 in a decentralized fashion, right? So if you take a look in here, this is a really simple example of a dApp in Cartesi. This is an echo dApp. Basically what it does is whatever you throw at it, it just throws back at you, okay? And if you're into Python, you can see that this code is, looks just like any regular Web2 Python code, right? That's because we wrap the whole framework and how you interface with it in a simple HTTP interface. And that has a couple of reasons, because most developers, they're not Web3 developers, right? You have a really steep learning curve. And in order to make it easier for Web2 developers to onboard, we made the decision of providing this nice HTTP interface. You comply to it, you're used to it, and now you have a decentralized application, right? This is just a preview. I'll just explain stuff and go back to this later, okay? So let's go from overview of Cartesi. Basically, we're bringing this new OS, and we think it's pretty neat. So we love Ethereum. Ethereum has security. It has decentralization with censorship resistance. We have all these thousands of nodes validating everything. Anyone wants to tamper with something, it's really hard because you have to lie consistently with thousands of nodes in order to do this. But Ethereum also has its drawbacks, right? Because since everyone on the network is validating everything, it means that all the nodes on the network are producing all the computations, and that makes it very limited. Because if you have the Ethereum network and you don't have tiny transactions, well, just throw a while one loop at it. You just halted the entire network, right? Or if you don't make it really, really expensive like this, well, then you can just flood it with useless tiny computations, and you halt the network anyway, right? So the idea on Cartesi is, can we get these really nice security guarantees of the blockchain, but enable really, really large computations, and also bring better tooling for development, and that's what we go for, okay? So how do we do this? Well, basically, what we do is have this special VM, we call it the Cartesi Machine, and this Cartesi Machine provides a Linux runtime environment. And the computations that happen inside the Cartesi Machine are secured by the blockchain, right? So this Cartesi Machine is based on RISC-V, and what happens here is RISC-V is an open hardware specification done by the guys at Berkeley, and it's really similar to what we have on our computers or on our cell phones, right? And because of that, it's compatible with Linux. And another thing we do is that, unlike in Ethereum, in which everything is running on the same VM, so the AVM basically is running all the applications. If some applications use more resources, using a lot of things, the other ones lose it. We have a VM per application. So a VM per application with a regular processor and Linux, well, we just enable a lot of things for you to use in there. And the Cartesi Machine, in order to do this, needs to be deterministic, so we put a lot of effort on making this RISC-V-based machine deterministic, like clock, floating point instructions, all the stuff that could generate entropy. We just had to make it deterministic. And yeah, as I was saying, to reach this stage in which you have a lot of computational resources, what happens is we rely on local consensus. And we have a rollup solution on top of it. So what happens is that, unlike in Ethereum, in which everyone on the network is validating everything, on Cartesi we have different sets of validators per application. So if you're interested in an application, you can validate it. If you're not, you just let it go. You don't have to watch and validate everything that's going on in the network, okay? And as I said, so consensus is basically really strong on Ethereum networks, because if you want to tamper with a computation, it's really hard to lie, because you have a really large amount of nodes. And I just told you guys that in order to scale, what we do is not everyone validates everything. So you can have a really small subset of the network validating a certain application. So how do we keep it secure? So basically, when there's a dispute and you don't agree with the result, it's not a matter of a local consensus with the people that are validating that application, and you just pick up the majority, and that's a consensus. No. What we have is a dispute protocol. We call it the verification game, in which whenever there's a dispute, what we do is basically the people that are disputing, since they are running the same application on the same Cartesi machine and it's deterministic, they should reach the same result. If they didn't, it means that at least one of them did something that they shouldn't. So we have this interactive protocol called the verification game, in which it has two parts. So the first part is it tries to use this Cartesi machine on both parties off-chain, and they post a signature of the state. So we basically pick up all the Cartesi machine state with RAM, disk, even processor state like the instruction counter, everything. We map it to RAM, and then we divide it in 4K pages. And these 4K pages are hashed, and those are the leaves of a Merkle tree. And then this root hash of the Merkle tree represents the whole state. And you use this to check if you agree or not with the state of someone else's Cartesi machine. So when there's a dispute, what you pick up is you pick up the whole computation. Let's say we have, I don't know, 1 million, for instance, cycles on that computation. So we do an NR search to search what's the first instruction we don't agree on. What we do is, okay, I'm going to post my root hash of the Merkle of the Cartesi machine at 100 million cycles, 10 million cycles, sorry, 20, 30, 40, up to 100. And then you're going to tell me, okay, so up to 40 million, I agree. 50 million onwards doesn't match. So now we know the divergence is between 40 million and 50 million. Then we drill down. So 41 million, 42, 43, 44, up to 50. And we go there. And each time we divide the search space by 10. So in logarithmic number of interactions, I'll know it's instruction 43,003,007 that we don't agree. Cool. Now we know the instruction we don't agree. But who did it right? Because I'm claiming something, you're claiming something else. That's the real special part. So what we did, and this is the second part of the process, is whenever we reach that instruction, it's not my word against yours. We just pick up that instruction, and we have an on-chain implementation of the Cartesi machine. So we had this huge effort of making an on-chain set of contracts that can emulate each instruction of the Cartesi machine. And this on-chain emulator is the one that actually picks up that instruction and executes it. So it's not me, it's not you, it's the thousands of nodes on Ethereum or whatever base blockchain we're using that are going to say who did the execution right. So this way, we can have a really tiny set of validators and computations, really large ones, but still maintain the guarantees of the strong guarantees of security of the blockchain, right? So as I said, it's an optimistic loop solution in which we build. So basically, we do all these computations inside the Cartesi machine, and from time to time, we just pick up the signature of the Cartesi machine and put it on chain. If someone disputes it, okay, there's the verification game. If not, we move on, that's set on stone, and you can keep up the computation for the next stuff. So how's the development of this? So you guys are used to Web 2. Web 2 is really simple. You have a browser, you use some framework like, I don't know, Angular or React or whatever you want, the tools, HTML, CSS, JavaScript as base technologies, and you do these nice interfaces, and then you interact with a backend, right? Generally using HTTP or HTTPS, and then you have a service. This service might use a database, might use someone else's API, this kind of stuff, right? Really simple. Now when we go to Web3, we still have a similar front end, but now we need a special library to interact with the blockchain. Generally, we have something that implements the JSON RPC protocol, so Ethers, Web3.js, something else, and then instead of talking to a backend, this guy is actually talking to the blockchain, like a node on Ethereum, or maybe a broker like Infura or Alchemy or something like that, right? And as you guys know, you have multiple limitations in processing all this stuff. It's hard, very hard to look for data. That's why we have services like the Graph and stuff like this, which are very popular, help you on the indexing, this kind of thing. And how does it look when you develop with Cartesi? Well, Basically, you still have your front end in which you use whatever technology you want. So if you have a browser, you can still use Angular, Vue, or React, all this stuff. And then you have a set of libraries to interact with the framework, right? And this framework there, then it has a really nice machinery, which takes all the abstraction of the verification game, of all this stuff from you. And inside the Cartesi machine, we actually wrap, as I told you guys, all the framework on an HTTP interface. So we have this HTTP dispatcher service, which is the one that you're talking to when you're developing your application. So from your development point of view, you're just talking to a HTTP interface, and that's it. You don't have to care about the blockchain, about reorgs, about any of that. We take care of that for you, okay? So just going a bit deeper on how this works. So those libraries I said, they basically use 3 different interfaces. So we still need a JSON RPC to talk to the blockchain, because whenever you're trying to reproduce a computation, well, you need the inputs, right? So you have a data availability problem if you're not using the blockchain. Let's say I'm storing my input on IPFS, for instance. And then you say, I cannot do your computation. Why? I don't have the inputs. Okay, from the blockchain point of view, there's no way for you to say, it's me lying about it not being RPFS, or it's you lying that you didn't put it in there. So that's why we need a JSON RPC interface, and we provide inputs through the blockchain. The second interface we use, is a HTTP REST interface, and that's used for something equivalent to Ethereum calls, right? So we have this inspect interface that on this inspect interface, basically, we allow you to directly talk to the Cartesi machine without any fees, anything. It's just HTTP connection directly to it, and you can do whatever processing you want to query for state. So let's say you have a chess game, for instance. If you open an application on a mobile phone and you want to know if you have ongoing games and what's the state of the game, you probably need your client to go there and look at a GraphQL with something you're indexing, or go directly to the blockchain, check that you have a transaction in which you started the game, check all the moves that other players did until you have the current game state and you're actually good to go, right? So this inspect interface is to handle things like that. So instead of doing that, what you do is you go through this inspect interface, you just call it the Cartesi machine, you give your address, and you say, hey, what's up? And then inside the Cartesi machine, you can process it on whatever language you want, Python, C++, regular backend, and then you can check, oh yeah, you have an ongoing game because I started it in the database, and yeah, this is the game state in a JSON, and it's white player's turn. So much easier than just going to the blockchain trying to reconstitute the data, or using something like the graph to index a lot of data, right? And the third interface in there, which is the graph, is an interface that we use to ease the outputs of the Cartesi machine. So the Cartesi machine basically can use reports, which is something you generally return when you're using this inspect interface. Then you have notices. Notices are a mechanism really similar to what we have on Ethereum events. So when you want to have a statement and it makes sense forever, like I won this match or something like this, notices is what you want to go for. And then we have this third interface, which is vouchers. So what vouchers are is a way for you to emit a transaction to interact with the blockchain from within the Cartesi machine. So since the Cartesi machine is deterministic and doesn't have outside the interfaces like internet and stuff like this, inside the Cartesi machine, you just do your transaction, and then you put it on a voucher. And the voucher is a really cool mechanism because you query it on GraphQL. Anyone can enforce it because, after all, it's a transaction that's signed by the application itself. And then we have an incentive mechanism that when you submit the voucher and enforce it, you get rewarded by it. And we got all these nice smart contracts on the framework that check if the voucher is valid, if it was submitted already, and all these guarantees that we should have, right? Okay, so let's go back to that initial code. So how does it look like? So basically, this is an echo application, as I said. It's a really simple one. Whatever you throw at it, it throws back at you. On the left side, we have an example using this front-end console that's available on our repo. So the URL is down here, but you can also query me for that later. Also available on our site. So it's a simple application done in TypeScript that basically implements all those three interfaces as shown. And on the right side, we have a basic echo application written in Python. So that's the actual decentralized code, right? So what we have in here, if you take a look, is first we start using this front end and sending a payload. So hello there. So from the blockchain point of view, we don't know what it is. It's just a binary output, binary input, but your application knows that's a string, right? So inside your application, that's regular Python code, as I said. So we're importing OS because after all, it's a Linux machine. And that service that I mentioned that has all the wrappers in HTTP interfaces, well, basically this server is listening somewhere, and we settle an environment variable with it. So we're using OS environment to load up that variable, and we also use requests. So people familiar with Python know it's a really well-known HTTP library, right? And okay, using that OS, now we're picking up that environment variable, so we know where to connect on the Cartesi HTTP servers. And now we have this dictionary here in which we settle advanced state and map it to a method called handle advanced, and inspect state and map it to handle inspect. So advanced state and inspect state are a payload. Whenever you receive an input on the Cartesi machine, it can be from two different sources. So it can be this input that came through the blockchain and is actually advancing your application state, or it can be a direct query you do. For example, that chess in which I said, so do I have a game, something like that, inspect calls, it will come with this metadata as inspect state. So you know it's something that's going to be thrown away afterwards, right? And the basic structure is you have this infinite loop, and this infinite loop has an iterator, okay? In this iterator, you're doing two things. When you call that finish endpoint, you're putting a payload that's saying what you did with the previous input. So let's say we're playing chess, and I just do a legal move with the queen. Well, it shouldn't happen, right? So you refuse this input. So in that payload, you're going to say that the status is reject. Now, if you provide me with a valid input, I'm just going to accept it, and that's the input of this endpoint. Now, what's the response? The response only comes when there's something to process. So once you call this guy, it just pauses the Cartesi machine, and the Cartesi machine is woken whenever the framework has something new for it to process, either inspect or a new input for the blockchain, right? And well, this response there, then you parse it. And as I told you, you have a special header in there, request type, which can be either advanced state or inspect state. And given that, we're going to use that dictionary in there to map to the right method to handle it. And then we just call this method. So handle advanced, which is the one we call in case it's advanced state. It's an echo application, really simple. So it just picks up the payload that you received. It creates a new dictionary with a payload entry and putting whatever you received in there. And then, once again, a simple call. So you do a post on this notice endpoint with the payload that you just set on that dictionary. And that's it. You just emitted your first Cartesi event, which is a notice, with the payload you received from the blockchain itself. And you return accepted because, well, that's valid, so let's go forward. So on the handle inspect, which is the case for this inspect API, which is ephemeral, same stuff. Only that this time we're picking up this payload and we're putting on a different endpoint on report. Report is this other interface in which I told you guys that it's meant to be ephemeral. So whenever you do a report, it's not stored, it's not there forever. It's like an Ethereum call response, right? And yeah, that's it. After you process it, we just set up that finish status to accept or reject and do it again. So now on the left side, once we process this, what happens is we emitted a notice in there, right? Because we just sent this payload through the blockchain, hello there. We got in there, and a notice was emitted. So we can still use this front-end application and use this really nice command, yarn start to notice list. And what this does is it goes to the Cartesi node, to the graphical interface, and says, hey, show me the notices. And there it is. You're going to have a notice, You're going to have a notice stating the epoch, input, and notice index. And the payload is in there, hello there. So epoch is because we're an optimistic roll-up solution, right? So all these time frames in which we validate stuff and then we roll up, those we call epochs. So that's the index of the epoch. So in a given time frame, you can have multiple inputs. So you have the index of the input. And then a single input can generate multiple events, right? So we also have another index for the notice there. Well, that's it. So basically, we have a tracking here which has a $10,000 USD price, and it's divided in three. So first place takes 5K, second place takes 3K, and third place takes 2K. We have multiple resources available to help you guys. So first of all, we're here. So you can just come at our booth and talk to us. We also have multiple examples of code, like we have this getting started, which is Echo in Python, in JavaScript, in C++, in Lua, in multiple languages. We also have some nice applications using machine learning or a database like SQLite, and yeah, a lot of interesting stuff in there, so you can give it a look. We have a special Discord channel for this hackathon. So if you scan our QR code on our booth, you get there. You also get a special badge that no one else would ever get, just people attending this event. And we also have the Cartesi docs available. So yeah. Once again, this is a hackathon, so you probably want to make some most tracks to have more chances, right? So if you want to mix our project with something else, let's say you want to do a slot machine, and you want to do it on top of Polygon, calling a smart contract on Chainlink for random number generation, and then you want to feed it to Cartesi Machine to actually do the slot machine. So you won jackpot, or you didn't get anything, or something like that. You can always come and discuss with us, and we can help you integrating stuff and figure it out, right? That's it. Hope you liked it. If you have any doubts, anything, just talk to me later, or you can stop at our booth. And yeah, hope to see you guys doing something really nice on this hackathon. Thank you.
Can you go back to like the starting of the slideshow?
This one?
Starting of the slideshow. Next slide. The flow charts.
This one?
Yeah, this one.
Okay.
So let's say for the Ethereum network, right? It is more secure because you need more nodes to, like, there are many people, right? So you need more than at least half of the chain to for the request to get through, right?
Yeah, basically when you reach consensus,
exactly.
It's true, and you need most of the network.
So
Yeah.
with Cartesi, we have different for different CMs, we have different computers. So like DApp A will have its own set, DApp B will have its own set, right?
Yeah.
So less number of members also does mean that it's more susceptible to like monopolizing, right?
Yeah, as I said, if we just use consensus, so like I'm playing poker with you and two other guys, right? If I just ask, okay, so what's the winner? And then if we have like 3 people saying one guy is the winner, well, he's the winner, and that's easy to manipulate, right? You just have to temper it with 3 people. But as I explained, whenever there are disputes, we don't rely on the consensus of the nodes that are involved in that computation. We actually engage on this verification game, and then the consensus is based on the execution of that instruction that we came together as the divergence instruction. And this is done on-chain, on a blockchain with thousands of nodes like Ethereum. So I'm playing with you and 2 other guys poker. We have a dispute. It's not us that's settling. We engage on this verification game, and this verification game runs on top of Ethereum or another protocol with thousands of nodes. And then even if the 3 of you are lying, but I'm telling the truth, I can still enforce the truth. So what's really nice on this protocol of ours is that you don't need, the security guarantees is not most of the nodes, it's at least one. So a single party can enforce the correct result. So we have a computation with 100 validators. 99 are lying, but a single party can still challenge them all and enforce the correct result, because in the end, it's consensus of the underlying blockchain that settles it, which in case can be Ethereum, Polygon, Gnosis, even other roll-up solutions like Optimism or Arbitrum.
Thank you.
Yeah. Anyone else wants? Okay.
When you're using a database, that database will be public, right? And if you're encrypting from the Cartesi machine, will we store the key also in the Cartesi machine, or how does it work?
Okay, so basically, the Cartesi machine can have the size you want as long as the validator is willing to store it, right? So you can think of it kind of like a decentralized AWS, right? So you set your application. You say that your Cartesi machine is, I don't know, 2 gigabytes of RAM, for instance, and 10 gigabytes of storage. And then you say, I'm willing to pay XCTSI per epoch validated. And then on the other side, you have validators that will say, okay, I'm willing to store this Cartesi machine. I have the resources. And yeah, I'm willing to be, to validate each epoch for the amount that you're proposing. If not, then you should probably raise your fee and actually have a group of validators wanting that. But going back to the storage itself, so basically the validator is holding that Cartesi machine, which in practice is a Docker container with this emulator inside. And if he wants to store like a Cartesi machine that has 10 gigabyte database, that's fine. And yeah, the database would be stored inside the Cartesi machine, so off-chain. So you don't have to pay for a lot for storage and stuff like this. Did I answer your question? Okay, awesome. Anyone else got a question? Anything? Okay, awesome. It was great talking to you guys, and well, looking forward to whatever you're building. Have fun.